Hello everyone, welcome to IIT's Gate classes. So in today's video session, we are going to see our continuous controller. So in the last class, we have seen your discontinuous controller or multi-positions controller like on-off control, three-position controls. We have seen what is on-off control, open, close, bang, bang, three-position control, as well as time proportional controllers we have seen few questions also. So if you haven't watched that lecture, kindly watch that lecture first and then start with this lecture. And if you haven't subscribed to our channel, kindly subscribe to our channel. And if you like this video, please press the thumbs up button and share this video with your friends. So what is continuous controller? So continuous controller is actually the natural extension of multi-position controller. So here basically what we have that your control action, it is basically continuous function of time. Like in your on-off control, we have only two positions. Okay, so in two positions, our controller can operate, but in continuous controller, it can operate in multiple positions such that all the positions, when we include it, it is actually a continuous graph. So there is a smooth linear relationship. Okay, so there is a smooth linear relationship between controller and the error, or I can say there is a continuous mathematical function relating your error and the controller output. Based on our syllabus, we need to study three types of continuous controller and their combination. So the first one that we have is your proportional controller, which basically generates output based on the instantaneous error. That means what? Output of this controller, it is directly proportional to the error. Next, in integral controller, basically my output of the controller is based on the cumulative of error, or you can say output of the controller, it is basically your area under the error curve or integration of the error or cumulative summation of the error. So we know summation in continuous domain, it is actually integration. So that is why I have kept integration over here. Derivative controller or D controller basically generates output based on the speed at which the error is changing, or basically output of the derivative controller is directly proportional to the slope of change of error or derivative of the error. So now these error are basically function of time. Okay, so that is why over here we have these three cases. Now based on this, we have combinations like P, I, proportional integral, proportional derivative, and proportional integral and derivative controller. So we will see one by one where these controllers are used and what are the advantages of using this controller and what are the shortcomings of this controller. Let us see one by one. So what is P controller? I told P controller is basically what? It is the natural extension. It is the natural extension of multi-position controller. So just like on-off control, in on-off control or in multi-position control, we have step changes, means my controller action, these are in step changes, whereas in P controller, what I have is a smooth linear relationship between your controller output and error. Okay, controller output and error, we have a smooth relationship. So there is a smooth linear relationship between controller output and error. Okay, so this is what we have in P controller. Now the dynamic behavior of the P controller after a step change in error. Suppose if I have a system. So this is my controller. Then we have final control element. Or let me do what? Let me merge the controller and final control element in just a single block, and let this be your process. So if I have feedback elements over here, so if this is my error, so if there is a step change in error, okay, step change in error, P controller, what it will do, it will basically generate one dynamic behavior or a step change in error will be generated for a P controller. Now the amplitude of this P controller, it is basically this amplitude, it is determined by the magnitude of this error. If magnitude of error is more, this step change is going to be more. If magnitude of error is less, the step change of the error will be less. Okay. So basically in your P controller, what we have, this is my controller output P of T. So P of T is directly proportional to what? It is proportional to your error. Now, if I remove this proportionality constant, I need to put something over here. So Kp I am putting. So this is your what? This is your proportionality or P controller constant. Okay, proportional constant we have over here. Okay. So now let us try to understand. Here I have drawn. Let us try to understand with an example. Okay. So this P of T is what? This is output of controller, and this E of T is what? It is my error. Now let us assume my error is something like this. First, let me copy this down because I will be taking one more example over here. So now basically what I told that output of the controller, output of the controller, it is directly proportional to what? It is directly proportional to the error over here. Okay. So now you can see there is a step change in error. So to minimize this, what will happen? My controller or P controller, there will be a step change. Now the magnitude of the step change, it is basically depending on what? It is depending this magnitude or the step change. This basically depends on the value of Kp. If value of Kp is higher, what will happen? The step change will be more. If value of Kp is less, this step change, it is going to be less. Okay. Now, if suppose my error, it looks something like this. So how will my controller take action for this one? For my controller, it is going to take similar kind of action. Now, if my value of Kp is more, suppose this is for one of the value Kp, KP1. Okay, let us assume this is KP1. Now, if there is one more controller where KP2 we have and KP2 is greater than KP1, then what will happen? Basically, this step change will be more. This will be my KP2. Okay, this will be the controller output with respect to time if my KP2 is greater than KP1. Okay, so this is what is we are having. So what I told, if KP value is high, then the rising gradient will be steeper. Okay, rising gradient will be steeper. So now you might be wondering why, if this is the case, why don't we keep the value of KP higher? See, if we keep the value of Kp higher, then what will happen? This rising gradient or this step change, it is more, as I have explained. Now, what will happen? Even if there is a very, very small change in error, your controller will take very large action. Okay, so it will have very, very strong action. Now, if I want to draw this Kp value, so you can see. So if this is my Kp2, then my Kp1, it will look like this. So this is what? This is my Kp2. So controller action will be more. Now, one thing you might be wondering, that why there is a steady state error. Why there is a steady state error. Now, ideally, when error is zero, what will happen? See, basically controller, it will not generate any output. P of t will be 0 because P of t is equal to Kp into t. So what will happen if my controller is not generating any output? This loop, it will not be closed, so process is not going to happen. So there shouldn't be any output from this P of t or controller output. It will not be generated if there is no small error. So that is why, to keep the system working, to keep the system running, what we have, we need to supply some energy or some error. There should be some error. Okay, so that is what we call a residual error we have. You can see in each of the diagram, I have kept some residual error. This residual error is actually kept so that my system keeps on running. So this is what is asked, when actually in your P controller, why do we need to have a residual error always? So that to keep my system running. So my equation, governing equation of P controller, it is P of t is equal to Kp into t plus P naught, sorry, t I have written, Kp into EP or error E of t, Kp into E of t plus P naught. So this is what we have. And why I told why this P naught we require, because if P naught is not present, if error is zero, this controller, it will not generate any output, and there will be my process, it will not be running, which will cause trouble. Okay. Now, if Kp1 greater than Kp2, what does this signify for a P controller for the same amount of error? Already I have explained, this is your PSU interview question, that if Kp1 is greater than Kp2 or Kp2 is greater than Kp1 in our particular example, what will happen? So I told what, if Kp1 or Kp2 is greater, so basically the rising gradient will be steeper. The rising gradient will be steeper. Okay, rising gradient will be steeper, which causes which will cause even a small error to have large deviations. Okay, large deviation, or I can say large control action, not deviation. Okay, we will have large control actions from our P controller. Okay. Next, very important topic we have is what? We have your proportional band and proportional gain. So what do we mean by proportional band and proportional gain? Then let us. So basically, this proportional band or proportional gain, it is the range of error that keeps the controller output between 0 and 100%. So this controller, ought to be very precise, P controller, its input is error. Now this controller, it is giving output to your final control element. Now final control element, it can be a valve, it can be a solenoid, it can be a relay, it can be anything. So basically, what is the range of error which can operate this valve or anything, any final control element from 0 to 100%? That is what is known as proportional band or proportional gain. Okay. So now if suppose I am taking one example of your fulcrum. So if I have a lever such that fulcrum is placed in the middle, so what will happen? Let us assume in this side we have error and this side over here we have controller output. Okay. So here you can see basically 0% change. Sorry, let me write it like this. 10% change in error will cause 10% change in controller output. 20% error will give 20% change in controller output. Why? Because my fulcrum is in the middle. Now, if suppose I keep the fulcrum towards I shift it towards right hand side. So now what will happen? Basically, for a small change in error, the controller output, it will be less. Suppose if I change by 10%, we know that for here basically for lifting small loads, sorry, I told you the wrong thing. For lifting heavy loads, suppose I have a 100 kg load, and if I want to pick this, what I will do, I will put a rod over here and I will keep the fulcrum here. So even a small change over here can shift this 100 kg load. So what will happen if I suppose 10% change in error will cause 20% change in controller output. 20% change in controller output. That means what? 100% change in error will cause 200% change in controller output. 200% change in controller output, I am assuming. So that means what? Kp over here is near about double. Now if suppose my fulcrum, I have shifted it towards left. So 10% error, now this time, what will happen? There will be 5% change. 5% change in controller output. So this we can understand. Suppose this is a 100 kg load. Now if I keep the fulcrum someplace over here, I keep it. Okay. Now what will happen? A very huge amount of force I need to apply to shift this 100 kg load. So that is what is happening. For a 10% change in error, 5% change in controller output we have. Suppose if 100% change in error will cause just 50% change in controller output. So this over here in this case, previously in this case, Kp was equal to 2. In this case, Kp is equal to half. Okay, Kp is equal to half. So now what is this proportional band? Proportional band is basically the range of error. Range of error that keeps the controller output between 0 and 100%. So in this case, 100% change in error was causing 100% controller output. So basically my proportional band in this case, it will be what? Proportional band over here will be 100%. What is the proportional band over here? Proportional band, as you can see, 100% error is causing 200% controller change. So proportional band over here is what? It is equal to 200%. And over here, 100% change in error is causing 50% just change. So that means what? Proportional band, it is what? It is the range of error which keeps the controller output between 0 and 100%. So controller output is just 50% when I apply 100% error. So this is what is concept of proportional band. Okay, proportional band. So now if, sorry, I have made a mistake over here. Kp will be half at this point. Why I am telling? Kp will be half at this point and Kp will be 2 over here. So now my formula for percentage proportional band, it is equal to actually 100 by Kp. So now put over here, Kp over here is 1 because 1:1 relationship is there. Here 1:2 half relationship is there, means what? 100% is causing 200% or 200% controller change is causing 100% error. So in this case, if you put percentage of proportionality band, it will be 100 divided by Kp. So Kp if you put half, so this comes out to be 200%. If you put this over here, so percentage of proportionality band, it is 100 divided by 2. So that is 50%. Okay. So that is what we have derived. Okay. So I hope there is no doubt up to this point. Now proportionality band, there is also one more definition. Proportionality band, it is actually equal to range of error divided by full span. Full span of what? Full span of controller. Means whatever is the maximum value minus minimum value of the controller we are taking, that we call it as proportional band. Now let us understand this with the help of an example. Suppose if I have a relationship like this, suppose I have 3 kp, okay, 3 kp, and one of them is like this. Okay, so now so basically what I told, range of error divided by full span. See, look over here. What I have written, range of error by full span of the controller is what? It is your proportional band. So that means what? Or if you want to write it like this, Kp will be equal to what? Kp will be equal to full span of controller, because Kp and Pb are inversely proportional. Full span of controller divided by range of error. Okay, so that means this slope is actually your Kp. This slope is Kp. So here you can see basically this is my proportional band, range of error that keeps the controller output between 0 and 100%. These are all your 0 and 100%. So controller output in percentage I should write. So this is PB1. Let me assume this is PB2. This is PB3. Okay, PB3. Now this particular case, you can see this particular case is that of this one, 50%. Okay, so proportionality band 3 is greater than proportionality band 2. You can see this is less. Sorry, proportionality band 1 greater than proportionality band 2. This one. Now, if I talk about KP and proportionality band are inversely proportional to each other. So, KP3 will be less compared to KP1 less than KP2. So you can check from here also. KP over here, KP3 means I have told this case. So this was what? This was basically, sorry, this case. So here we have half, then we have 1, then we have 2. Okay. So proportionality band means what? Proportionality band is the range of error which keeps the controller in 0 to 100%. Now what will happen if Kp goes to 100? If Kp goes to infinite, Kp goes to infinite, this line, it will go something like this, keep on going. So when Kp goes to infinite, basically this implies that we have on off control. Okay, so remember this, if Kp is going to infinite, we have is on off controller. So at no load condition, I told error is 0. Okay, error is 0. But to keep the process running, we cannot make the error 0. So that is why you might have seen that P controller at steady state has permanent steady state error. Permanent steady state error. This we always have for what? We have it for your P control. Okay. So any doubt up to this point, please let me know. Any doubt? So now already I have explained P controller at steady state has a permanent steady state error, and this is called as offset. So let us understand this with the help of an example. So now let me take few examples. So first, let me assume a system which has Kp, something like this, is the input to the system. Okay, so this is what? This is my Kp1. Let I have one more system. Let this system be Kp2. And let I have one more system which has Kp3. So now let me ask you, you can see over here that all of them have some offset error. Okay, offset error. Now you can see, you can tell me also that Kp1, it will be greater than Kp2, it will be greater than Kp3. Why? Because you can see the control action of Kp1 is more to the same amount of error. See, error I have kept same in all the three cases. So basically what I am telling is that proportionality error over here is more, Kp is more compared to Kp2 compared to Kp3. And why we need this offset? Already I have explained this to you. Now we have here over here is a simple question. Let us try to solve it. So what is the question? A proportional controller is used to control the height of a water in a tank where water level can vary from 0 to 9 meter. Okay. So we have a tank where the water level can vary from 0 to 9 meter. Suppose this is 9 meter and this is 0 meter. 0 to 9 meter. So now what is said? Calculate the value of proportional band. We have to find PB and KP that will set the water level at 5 meter. That will set means my set point is 5 meter. Set point is 5 meter. The controller is to fully close the inlet valve when the water level rises to 5.5 meter. So whenever water level is going to 5.5 meter, my controller output will go to 0% and fully open inlet when water level falls below 4.5. So if it falls below 4.5 meter, controller output will be 100%. So this is what is said to me over here. So proportional band is equal to what? It is equal to range of error divided by full span into 100. So this is what we have. So range of error, you can see error is what? See, 5 is my set point. So above 5 and below 5. So 5.5 minus 4.5, okay, divided by full span. What is the full span that we have? Full span of output 0 to 9. So 9 minus 0 into 100. So this is what? This is 1 by 9 into 100, which is equal to 11.1%. Okay, 11.9%. So now percentage of proportional band. So this is in percentage I have calculated. So percentage of proportional band, this is equal to, remember, 100 by kp. 100 by kp. So over here we have this as 100 by 9. Okay, 100 by 9% is equal to 100 by kp. So value of kp comes out to be as 9. So this is my answer and this is my answer for this particular question. A very, very simple question which was asked in your previous year GATE exam. Okay. So next question that we have over here is figure A. So figure A depicts below the controller output versus temperature. You can see controller output versus temperature behavior for a proportional controller, and figure B depicts controller output versus error, percentage error. Calculate proportional band in each case. Set point given is 150 degrees C. Okay, set point given in both the cases is 150 degrees C. So here you can see this is controller versus temperature, this is controller output versus error. So in both the cases we need to calculate what? We need to calculate proportional band in each case. So let us try to calculate proportional band using figure A. So in figure A, proportional band, we know that what? Range of error divided by what? Full span into 100. So range of error we have is set point is 150. So range of error, you can see it is this one. Okay. So range of error is 199 minus 151.2. Okay, 199 divided by, sorry, minus 151.2 divided by span. So what is my span? Span is the total range of my output that we can have. So that is 300 minus 60 into 100. So this is what? This is near about, sorry, 150, 199.2. Okay, 199.2. So this over here we have is 48 divided by 240 into 100. So this comes out to be, if I divide it by 24, so 24 to 10. So this comes out to be 20%. So proportional band comes out to be 20% using figure 1. But if this figure 2 was or figure B was given, how to calculate proportional band from this case? So we know that EP, percentage of error, is equal to what? It is equal to, we have seen the formula, R minus C, set point minus actual output, divided by range or span, I can say C max minus C mean. So R is what? Let me calculate for this one. Okay, let us calculate for this particular case. So R set point is 150. C is what? C over here at this particular case. At this particular case, what is my C? You can see from here that it is 151. So 150 minus 151.2 divided by C max minus C mean, that is 300 minus 60 into 100. Okay, so this will come out to be as your, I think, let me use calculator over here. So this comes out to be 3.66%. Next, let us calculate the percentage of error for this. So here set point is once again 150 minus at this particular point, what is the output actual? 199.2 divided by 300 minus 60, that is 240 into 100. For this, let me use calculator. So this comes out as minus 16.33. So this is what was given in the question. So if in the question this is asked to you, so basically proportional band is what? It is the range of error for which controller output swings between 0 to 100. So 0 to 100, for 0 range of error is 3.66%, minus 100, for 100% it is 16.33. So if you add this two, it will come out to be approximately 20%. So if in the question controller output in percentage versus error is there, you need to calculate, you need to see for 0%, you need to see for 100%, subtract the percentage error of percentage error of 100 minus 0, you will get what? You will get your answer. Okay, you will get your proportionality band. So this was also a very simple question that we needed to solve. Next we have over here is integral mode. So what do we mean by integral mode? Now let us see. So in this, basically the rate of controller output is proportional to the error. Okay, proportional to the error. Rate of, what I said, rate of change of controller output is proportional to the error. So now if we integrate both sides, so P is equal to integration of E dt plus whatever constant will be there. Okay, constant will be there. Now, integral mode or I controller is also called as reset controller. Reset controller. Why is it called so? You can see if if my controller output is constant, if my controller output is constant, what will happen? Basically, over here, my error will be 0. So whenever error is 0, understand it like this. Whenever error is 0, that means controller output is constant. So that is why it is trying to reset my error so that my controller output becomes constant or 0. Okay, controller output, if it is constant, so what will happen? Error will become 0. So in the previous case, see, by default, I had to keep what? I had to keep constant over here. Constant error I had to keep constant so that controller output was what? It was constant. But at this particular case, even if my error goes to 0, which is my constant value, my controller output, it is what? It will remain at a constant level. So I don't need to give what? I don't need to give offset error at this particular case. So as long as error is non-zero or even constant, the integral action will cause the manipulated variable to change. Okay, manipulated variable will change. So my governing equation is this. Now, if I use proportional, if I remove this, sorry, it will be like this. So if I solve it like this, okay, so let me write this as EI to differentiate that this is I controller. So if I remove this proportionality sign, it is going to be what? It is going to be Ki into E. Okay, Ki into E. Now, what is this Ki basically? Ki is equal to Ti, where this Ti is what? It is integral time. It is integral time, also called as reset time. And what is this Ki? Integral constant. Integral constant. It is called as integral constant. Now, if we solve this, integrating both sides, dp is equal to ki e dt, integrating both sides. So p is equal to ki e dt plus p naught. Now this p naught is what? It is constant. If basically this is given by controller at t equal to 0, basically what I told, see here, even if p naught is 0, my controller, it will keep on running. I explained it just needs a constant value, or even if error is 0, it will give what? My controller, it will get output. Suppose if I have error like this, so my controller output, what it will try to do, it will try to summate the error or integrate the error. So at this particular point, we know that for a ramp signal, my integration is what? Sorry, for step signal, my integration is what? It is my ramp signal. So it will look something like this. So this time is what? This is my Ti. Okay, Ti. So if error is 0, even if error is 0, it won't matter. Suppose if I draw it like this, you can see error is 0 over here in this case, but still my controller output, it will keep on running like this. Because what we have over here is integration of error. But one thing to note is that this response is quite slow compared to P controller. So over here in P controller, we have sluggish response. Sluggish response. Very slow response. Now, if this Ti is very large, Ti is very large, what will happen? For the small error, my change, it will be like this. For this particular error only, it will be very slow. The control action will be very less. For Ti, very high value. So over here, I need to keep the integral time low. Integral time I need to keep low. But if I keep it very low, what will happen? What will happen? It will cause instability. So what happens if Ti is high? My system is sluggish. If Ti is low, system is what? System becomes unstable. Why? Because I controller, it is basically what? Addition of pole at your origin. Addition of pole at origin. And we know that when we add pole to the system, your system becomes what? It shifts towards instability. So if my Ti is very, very high, this will look something like this. For this particular error only, it will go like this. Keep on going and going. My output, controller output, it will become unstable. Okay, so this is the problem with I controller, that basically if you need to set the value of Ti such that neither it is too low nor it is too high. Okay, and usually it is sluggish in response. So next we have a question over here, a very, very simple question. What is that? I want you to pause the video and solve this question. An integral controller is used in a temperature control in a range of 0 to 250 degrees C with a set point of 150 degrees C at zero error, EP equal to 0. The controller output is 20%. Reset rate is minus 0.1 per second per percent error. If temperature jumps to 180 degrees C, the controller output after 5 seconds. Okay. So here what is said, set point given is 150 and C, my actual output 180 degrees. Okay. So we know that P of T, it is equal to what? It is equal to Ki into E into T plus P naught. Okay. So now Ki given over here is reset rate is minus 0.1. Error, we don't know. Time, what is your time? So after 5 seconds it is written, so 5 plus P naught. So P naught given over here is 20%. Okay, so we need to calculate the controller output in percentage. Okay, controller output in percentage. So if we find out this E, we will be able to solve it. So let us try to find out E. So we know that percentage of error in controller, it is given by the formula R minus C divided by C max minus C minimum. So R over here is what? It is equal to 150. C is 180. C max minus C min is 250 into 100. So this is minus 30 by 250 into 100. So 0, 0 cancel. This is 4. So this is minus 12%. So we got minus 12%. Plug this over here. So minus 0.1 into minus 12. So minus minus becomes plus into 5 plus 20. So this is 12, 5, 60. 60 into 0.1 is 6. So this comes out to be as 26%. So we make a jump from 20% to 26% over here. So my answer is what? It is 26%. Okay, very simple question. So next question we have over here is, an integral control is used to level control with a set point of 12 meter. Set point given over here is, so start writing what is given. 12 meter. C max given over here is 15 meter and C minimum given to us is 10 meter. The controller output is 22% at set point. So it is 22% at set point. That means what? At set point, we know that at set point, basically my error is equal to 0. So this given over here is P naught, which is actually 22%. 22% is given. The constant Ki is given also. Ki given to us is 0.15% per second percent error. If the level jumps to 13.5, calculate the controller output after 2 seconds. Once again, same kind of question. So P of T is equal to Ki into error into T plus P naught. So Ki we have, Ki given is 0.15%. Error we don't know. Time given to us is 2 seconds. P naught is 22%. So error we need to find out. So error, basically it is what? It is equal to R minus C. So R is 12. C is what? 13.5. C max minus C mean is 5 into 100. So this is 20. So this comes out to be minus 1.5 into 20. So cancel. So this is minus 3%. Plug this over here. So minus 0.15 into 3 into 2 plus 22. So 6 into 1.5. So this comes out near about your so 0.15. Let me solve it. 100. So 5, 3. This is 20. 4. So half 1.5. So this comes near about your. I think I have made some mistake over here. I have made some mistake. So this is 30%. This is 30%. So if I plug this over here, minus 0.15 into 30 into 2 plus 22. So by 100, if I remove this, so 0, 0 cancel, 0, 0 cancel. So this is 45, 90. So 9 minus 9 plus 22. So this comes out to be as plus 13%. So the answer to this question is 13%. Okay, very, very simple question. So next we have over here is derivative control. So derivative control, in over here we have the controller of output directly proportional to the rate of change of error with respect to time. Okay, rate of change of error with respect to time. So now if I solve this, if I remove the proportionality sign, so P of T comes out as AD into DE of T. DE of T. So basically we have over here is what? We have over here is the derivative of the error or rate of change of error. So suppose if my error is something like this, then we know that for constant, if I take derivative, it is going to be 0. And at this particular case, you can see we have over here is something like this. Now derivative mode, it is called anticipatory. Why so? Suppose this time is T1, this time is T2. So you can see error at T2, let me assume it is E2, and error at T1 is E1. So you can see at this particular time T1, my controller has already taken action for removing whenever at this particular time T2 my error is. You can see over here. Okay, you can see over here that at this particular time only I have taken corrective action for T2, because at T2 this is what is the controller output. So whatever is my output at T2 means error at T2, controller has already taken action for that. Okay, so that is why this is called as anticipatory control. And over here my response is fast. Now you might be wondering, if this is so much good that we can predict the error and controller can take action, why don't we use it always? So there is a problem with derivative mode. Suppose my error, it looks like this. Suppose this is my error. Okay, this is my error. So what will happen if I take derivative of this? For constant, this is basically what? This is a step signal. So there will be just simple impulse at these 2 points. And controller output, they don't react to this impulse. Why so? Because impulse signal, we know that width of impulse signals are 0. So controller will not be able to distinguish the error, whereas we have error in the system, but controller, it will not take, D controller, it will not take any action over here. Why so? Because controller, it cannot detect impulsive signal. Why? Because the width of impulse signal is 0. So that is why derivative mode is not used single. It is always composite form, either PD, PI, sorry, PD or PID, not ID. We don't use ID also. Why? Because ID we cannot use. There is problem with that. Okay, we are going to discuss later on. So with this, we will be ending this session. In the next session, we are going to see all the composite controllers like your PI, PID, and PD. This we are going to see in the next session. So if you like this video, please press the thumbs up button and share this video with your friend. And if you haven't subscribed to our channel, kindly subscribe. And remember one thing, if you have any doubt, you can comment in the comment section below and I will get back to you. Okay. So see you in the next class. Thank you.